All right. Ladies and gentlemen, I was really inaudible before, but now I am. So, I started off with this simple concept that have you ever pushed a door while just being beside that axis? So, if for example you have this door over here and this is your axis, then you are obviously going to just push your door by the doorknob and not somewhere beside the axis. The reason is pretty simple and it can be explained by torque. Torque is nothing but the cross product of my position vector r with my force vector f, and the direction is given by the right hand thumb rule, which is the direction perpendicular to both the r and the f vectors. So the reason why I'm not pushing my door right beside the axis is because I won't be able to generate enough torque to rotate that door. You can try it out yourselves. I'm not kidding you. The reason why the doorknobs are at the rightmost end of the door is now pretty obvious, because the distance r, which is the moment arm or the position vector of the application of my force, is increased. And since my force is pretty much the same, the torque is going to increase and in turn help me rotate that door easily. That was how easy torque is. It is given by this formula r cross f, which can be simplified as rf sine theta, where r is also known as the lever arm, which is measured from the axis of our rotation. In rotating any object, the axis is crucial because it can rotate only about an axis, or if it's a complicated motion, then maybe it's not rotating about an axis and it's going straight as well as rotating. But for simplicity, let us consider that there is an axis of rotation about which that object is rotating. Furthermore, the direction of torque is given by the cross product or the right hand thumb rule, and that vector is perpendicular to both my position vector r and my force vector f. The torque is required to produce an angular acceleration, just as in the case of force, which produces a linear acceleration. And that angular acceleration in turn produces an angular velocity omega, which rotates that object through a angular displacement theta, which is all essentially just the linear motion, but just written down in the rotational counterpart of it. As you can all see, position x is translated to theta, v translates to omega, a to alpha, and so on and so forth. That is how we get all the required. So we are just deriving the same analogy from linear to the rotational part, and that's how easy it can be. All you need to do is just be clear about the linear motion wala section, and rotational motion is at your tips. Speaking of rotation, have you ever seen the earth revolve around the sun? Well, it does because of the seasons, and it's so important to have those seasons, right? And not to forget about all the other various other things which is happening because of this periodic motion around the sun. You heard me right, I said periodic motion, which means the motion is going to repeat itself, and hence we get the seasons every year. The more complicated periodic motion is the oscillatory motion, in which there is a to and fro motion about a point, and it is as well a periodic motion, no doubt, because it is going to repeat. But this motion is also to and fro about a point, and that point of suspension is pretty much like the axis, as you have all guessed it, for that object rotating about it. Then we next have equilibriums, which are stable, unstable, or neutral. What an equilibrium is, that in simple words, it's just when I'm just sitting on the ground or lying on my bed, I'm in equilibrium, or I'm in a state of rest, right? I'm not moving around, I'm not doing anything, and I'm just going to be there, and nothing is going to change that. Even if someone pushes me, I'm going to come back to the same place because I am in a stable equilibrium. But if I'm standing on a hedge and if I'm tilting forward, then after a point I'm going to fall over and tip over, because that is an unstable equilibrium. As you can see, these equilibrium types are pretty self-explanatory, and I need not say more about them. But You should know why they are so important. And in circular motion or calculation of torque, they are really crucial, as you can see that in a neutral equilibrium the object is going to stay there. In a stable equilibrium the object is going to keep toppling, but then come back to the natural state, while on an unstable equilibrium the object is going to topple over. The reason behind this is the vital thing which I'm going to really quickly discuss with you. That is because the center of gravity is producing a force of mg below. And if I'm tilting my cylinder a little bit to the left, then still my mg is the torque produced by the mg about this axis. So this is my axis. One of the ends of my tumbler is going to be the axis because the object is rotating about it. The torque produced by this force, so the perpendicular distance r, is not enough to entirely topple it over. What I mean is that if I'm rotating it like this, the torque produced by this mg force is going to take it back to its original configuration. Although, in such a case when the mg torque is acting in the opposite direction, so the cylinder is now tilted so much that the mg torque is now going to act on the other side. Instead of bringing it back over here, it's going to take it to the other side and it's going to topple over. That is pretty easy to visualize, because you have seen that if a cylinder is rotating in a small angle, then it's going for a periodic motion or a oscillatory motion. Could also be a simple harmonic motion depending on how much is the tilt of the angle. But if it goes over that threshold angle, and the torque acting because of my center of gravity or my mg is more than, it's in the direction opposite to the direction in which I want to go back to, or in my stable direction, then no one is going to stop it from toppling over. So welcome you all to Easy World Physics, where now you know what circular motion and torque and equilibrium and many more other concepts associated with it are inside your heads. Well, on the surface level, but that's okay. So just a quick recap of what we were doing last time. We were studying the Ampere's loop law. Fascinating as it was, let's just have a quick recap where I'm having a cylindrical wire. So it's a thick cylindrical wire through which current is flowing, and the current is flowing uniformly through it, as that is the only, so that needs to be the only assumption that we are making, because otherwise our Ampere's loop law is still valid, but we can't find out the magnetic field, as it gets really complicated. And for this, let's just calculate the field outside at any point B. So the field is going to be the same on this circular ring, and I simply know that the magnetic field mu naught into I is equal to the magnetic field ka integral which is simply the Ampere's law. Now I also know that I is the total current I is enclosed entirely inside this loop. It's passing entirely through this loop. So mu naught into I is essentially the current enclosed, which is mu naught into I. And B is constant throughout that loop, as it is following the circular symmetry, as it should be, because it's a beautiful part of nature. And why shouldn't it be? So B times integral of dl. And we know that integral of dl is nothing but 2 pi r, where r is my distance. So over here it's r dash. So let's just take r dash. And I know that the magnetic field outside is simply mu naught I upon 2 pi r dash. Similarly, if I'm taking a point inside my cylinder, so if I have this point over here, which is at a distance smaller, then it's pretty much the same thing, but my I enclosed is not going to be the total current I, because my loop is carrying only this much current. My loop is carrying only this small circular element of a current, the small cylindrical the section through it, which is the only current carrying passing through my loop, and that is all I'm going to consider for my Ampere's loop law, as that is what it states, that the current passing through my circular loop enclosed inside it multiplied by mu naught is going to give me the line integral of B and dl, B dot dl. So mu naught into I enclosed, and I need to find out what that I enclosed is. So let's just say that the total current is flowing is I through the cylindrical wire. Then I need to find out the total current flowing through this smaller section, which is going to be pretty much solved by unitary method. So if through pi capital R square the current I is flowing, then through 1 unit area the current flowing is I upon pi R square. Easy peasy. And the current flowing through this pi small r square area is going to be nothing but I into pi small r square upon pi capital R square, which is the beauty of it. And again, I'm just using simple unitary method, nothing else. And then you can find out that the current is, for this case, mu naught I small r square upon capital R square. Wow, I found out what the mu naught I enclosed is, which is equal to the B dot dl and the integral of it. And since B is again by circular symmetry or by cylindrical symmetry, but over here the loop is in a circular shape, so the circular symmetry is going to be followed, and the B is going to be taken out of that integral, and what I have is just again the integral of dl, and I know that B and dl are again tangential to each other, so B dot dl is simply B dl, and B is also out of that integral because B is a constant throughout my loop, and I just need to simply integrate the dl wala part, which is nothing but pi into 2 pi r, 2 pi small r, as I have taken this distance as to be r, which is equal to mu naught I r square upon r square. And mu naught I r square upon r square is my mu naught into I enclosed, and I see that some terms are getting cancelled out, and my magnetic field simply comes out to be mu naught I r upon 2 pi capital R square. This was the application of Ampere's loop law once again. Hi, stylish Rajput. I don't know how to pronounce your name, but I hope you're getting the Ampere's loop law. And I just found out that the current inside the magnetic field or the cylindrical wire is mu naught I upon 2 pi R square into R, and the current outside is mu naught I upon 2 pi R. So if I draw these graphs, as you can see that the field is proportional to 1 upon R outside my wire, while it is proportional to R inside it, and hence the graph is going to be linear till R is equal to R, which is the radius of my cylindrical wire over here, and after that it is going to be proportional to 1 upon R, as you can see. So these are the two relations, and drawing graphs is the mathematics. You know it. Maybe if you don't, then just watch my introductory video and welcome to Easy World Physics, where I've spoken about graphs and maybe you'll get a little idea. Now the homework problem. What was the homework problem? I gave you a simple problem that if a toroid, so again one more application and one more relation between toroid and the solenoid, which was obvious because they are pretty much the same thing but just in a different shape. But the toroid is having n, capital N, as the total turns, and I told you that the magnetic field because of all the total number of turns inside a toroid comes out to be mu naught n I upon 2 pi r. Right? You remember this? You remember this from the last class. Now, if for example I tell you that let's for a change keep small n, as in the case of solenoid, as the turns per unit length. Turns per unit length, as in the case of solenoid. So I'm just taking the same elements which I was using in a solenoid. So I'm taking the same terms like small n, and I was also saying that small r is the average radius. So what I'm assuming is that the toroid is, so if this circular shape is a toroid, I'm assuming that it is sufficiently thin so that my radius is an average radius, and it's the change because of the changing radius is negligible. And then what I was asking you to find out was that what is the relation between the magnetic field because of a toroid and the magnetic field because of a solenoid when I am applying the same terms from the solenoid. And the answer is pretty simple. As you have guessed it, since they are the same thing but in different shapes, the answer should be the same. And why it shouldn't be is it can't be. It can't be. It has to be the same. And the reason why is that if r is my average radius, then I can say that this distance from here over here is r. Then I can also say that so if I have the total number of turns as n, so the total number of turns is nothing but 2 pi r, which is going to be the length of one of my wires into the turns per unit length. So if I have n turns per unit length, so for example I have n turns over here and this is 1 unit length, then the total number of turns in that toroid is going to be nothing but the turns per unit length n into that length, and that length is 2 pi into small r, because small r is my average radius. So if my average radius is smaller, then this length, I'm assuming that throughout that toroid from this point inside till outside, like irrespective of the point, this is sufficiently thin, so the total length inside is 2 pi r, which is simply the circumference. And if I replace this over here, then what will I get is, as you know, as it should be, it's mu naught. So I keep 2 pi r into n into I. I'm replacing this n with this over here, and what I get is the same thing, mu naught n I. And I'm not surprised, as you should not be as well. But that was your homework for today and for yesterday, and you should have come with it today. Like Rajput करके आए हो क्या? ये सवाल कल दिया था. Have you attempted it? If you haven't, check out my last video and try it out once again. If you don't, then just anyways come for this Unacademy Combat scholarship test on 17th October. Mark your dates, mark your calendars. 30 questions in 60 minutes. I'm giving you just one, but here you have 30. तो थोड़ा सा टाइम लग सकता है, which is pretty much 1 hour, which is the length of my class as well. Test will be in Hindi and English, and you can win scholarships up to 1 crore, free live test on Android. And Sachin Tendulkar is saying that emerge join kar lo. You'll find the link below in the description where you'll get a detailed performance report. Top educators will be mentoring you, will align you with the latest guidelines, and you'll get the video solutions. And then furthermore, the dates for the mock exams are as follows. अगर आप 12th में, then these are the following. 10th में, it's these. Just have a look, enroll for free, link is below. And then the topic of the hour for today, which is the current carrying wires and loops. Now let's just see that, let's just assume that I have two wires like these. These are two wires, and they are just kept parallel to each other. They are two infinitely long wires. So this is infinite, this is infinite. The wires are extending till infinity, and I need to find out if both of these wires start carrying current in the same direction simultaneously, what will be the value of the force acting in these wires? What is the force acting on the other wire because of the first wire? And similarly, what is the force acting on the second wire because of the first wire? It's pretty easy, pretty easy. Just think about it. So why is there going to be a force acting? Because I know that if a charge is moving, it produces a magnetic field. The current carrying wire is nothing but moving charges, which is making a circular magnetic field, which I just found out for you like not even 5 minutes back. And we know that the magnetic field because of an infinitely long current carrying wire is going to be mu naught I upon 2 pi r, where r is the distance from the wire. Now, if I know that r is the distance, then over here that distance is h. So definitely the magnetic field due to wire number 2 is going to be at this point 1, and that magnetic field because of wire 2, so I'm going to say magnetic field because of 2 is equal to mu naught I2 upon 2 pi h, and that is going to give me my magnetic field at any point on wire 1 because of wire 2. Since they are infinitely long, I do not care like if the magnetic field is going to be any different over here or different over here. They are infinite in length. For both the wires, the length is infinite, so the magnetic field acting has to be the same. That is the symmetry of the infinites. And infinite is a mathematical concept, but in physics, what we mean is that we are making our life easier by ignoring the end points and the end results and just calculating the field due to the wire and making sure that it is the same throughout the wire. Since I have the magnetic field acting at this point because of the second wire, I also know that the force experienced by a current carrying conductor or a current carrying element is given by the Lorentz force law, which was Q into V cross B. Over here we don't have a charge, we have a current carrying conductor, and that current carrying wire is going to experience a force throughout its length, and instead of the charges I'm going to make sure that I use current into L cross B. It's the same thing but just written in a different form. Again, if you are not sure how I've written this, then just check out my previous lesson on in fact my second lesson on motion of charges under a moving field, moving charges under a field, and there I've explained to you in detail how we derive this equation and why are we getting pretty much the same counterpart, but instead of charge the current part is there, instead of velocity the length vector is there. And this is pretty much intuitive because charges are nothing but the current carrying charges are nothing but the current is nothing but the moving charges. I'm getting myself into a corner, but nothing to worry about. We are crystal clear, we know what we are doing. This is the Lorentz force experienced by a current carrying element of length L, and since now I also know by the right hand thumb rule that because of the second wire the magnetic field is, as you can see, moving in circles and also in a direction, if I'm seeing from the top, is anti-clockwise. So the magnetic field over this point 1 or on this point 1 is coming outwards. It's coming outwards, it's coming outwards, it's coming outwards, it's coming outwards everywhere on that wire. And if the magnetic field is coming outwards, the current I is in this direction, so my length vector is going to be upwards as well, as that is what the direction of my current is. The direction of the current is going to give the direction of the length vector. The direction of the length vector is upwards. The magnetic field is coming outwards. All I need to do is now apply my right hand screw rule or apply any other rule, but just find out that if L cross B is in this direction, if L is in upwards and I curl it towards B, my force is going to be towards my second wire. I can use the other two laws in which I'm going to get the same result, so you need not worry. I am doing the same thing with my left hand now, and I find out that the force is again going to be in the right direction. Use the palm rule, use the right hand thumb rule, use the Fleming's rule. I personally like the right hand thumb rule as that is the fundamental for cross products. And if you are getting a little confused about cross products, just check out my first lecture on Introduction to Easy World Physics, where we talk about position vectors. And in my next lecture, the Introduction to Magnetic Fields, we are talking about how cross products came into picture, like why do we even need them, and why were they invented, so as to say, like why were the dot products and the cross products came into picture, like why were they required, and what was their need. So since now we know that the force acting because of wire 2 on wire 1 is going to be towards the right, so I'm going to say this is the force acting on wire 1 because of wire 2. It is going to be to the right. I can also write it down as I1 into L cross mu naught I2 upon 2 pi h, as I know what the magnetic field is. So making my task even easier now, I know that the direction is going to be towards my right, so I'm going to just simply write down I cap over here and remove the vector. So I know that this is the force acting because of wire 2 on wire 1, which is given by I1 L mu naught I2 upon 2 pi h, and it's in the I cap direction. Similarly, can you tell me what is the force acting because of wire 1 on wire 2? And that is easier even than the first example. Then that is going to give you pretty much the same thing if you have already guessed it, because there's no difference in wires 1 and 2. They are the same wires, and it is also in this figure. So if you were not paying attention, then you can already see the solution over here. Not my intention at all, but I know that the magnetic field because of wire 1 on wire 2 is going to be inside, as I'm going to use my right hand thumb rule to get the direction of the magnetic field. So if current is flowing in this direction, then the magnetic field is going to go inwards, and if the magnetic field is going inwards, then the force acting on this current carrying element because of the first wire is going to be given again by the right hand thumb rule. So I'm going to use the L cross B, my L, keeping my hand in the direction of L, curling it towards B. The force is coming leftwards, isn't it? It surely is. So the force acting on wire 2 because of wire 1 is going to be in the left direction. So force acting on wire 2 because of wire 1 is going to be I2 times L mu naught I1 upon 2 pi h into minus I cap. I know the direction, so I need to specify it as well. The direction is now given, and I also know that since these two wires are getting a force towards each other, they are experiencing an attractive force towards each other, then the wires are going to get attracted towards each other, aren't they? The wires are going to get attracted towards each other, which means that they are experiencing force which is an attractive force, and What I can also say that if they are carrying current in the same direction, then they are going to get attracted towards each other, which is the opposite of the case of electrostats, in which similar or like charges repel each other, which is the key difference over here from the electrostats. So the reason is something which can be explained by relativity. I know the reason, but for now, just have a sip of water. It's important to be hydrated. All right. So I know that if the two current carrying wires are carrying current in the same direction, they are going to get attracted towards each other. Similarly, I need not explain this, but if the current is in opposite directions like this, they are going to get repelled from each other because the current is now in opposite directions. You can try that out. So if the force experienced by this wire because of this is in this direction, keeping the current same, I'm going to change the direction of my L vector. And since my direction of L vector has changed, I obviously know that if I'm going to apply my right hand screw rule, I'm going to change the direction of my force as well. So in this case, the L is going to be downwards. So L is downwards, magnetic field is upwards. So I keep my hand towards the direction of L, curl it towards my direction of the magnetic field, and the force is going to be in this direction. Similarly, because the current flowing in the first wire is now opposite of the first direction, the magnetic field because of this on the second wire is also going to be opposite. And even though the length vector is upwards, the magnetic field acting on that length vector because of the first wire is going to be opposite in direction, as the magnetic field, instead of going inside, is coming outside. That was the crux, and that was it. Just remember what all I have said to you right now. अभी तक मैंने आपको बस इतना बताया कि magnetic field is going to produce force between two current carrying wires, and if they are carrying current in the same direction, तो उन दोनों पे एक attractive force लगने वाला है. एंड अगर वो करंट ऑपोजिट डायरेक्शंस में कैरी कर रहे हैं, देन उन पे एक रिपल्सिव फोर्स लग रहा है. इसको याद करने का तरीका है इलेक्ट्रोस्टैट्स का जस्ट ऑपोजिट. इफ दे आर कैरिंग, अगर वो करंट सेम डायरेक्शन में लेके जा रहे हैं, अगर वो दोनों एक ही डायरेक्शन में ऊपर को लेके जा रहे हैं या नीचे को, तो वो दोनों रिपेल करेंगे, तो वो दोनों अट्रैक्ट करेंगे. इलेक्ट्रोस्टैट्स में लाइक चार्जेस रिपेल होते थे, यहाँ पे लाइक करंट अट्रैक्ट होगा, लाइक करंट अट्रैक्ट होगा. ऑल्दो अगर मैं अनलाइक डायरेक्शंस में करंट लेके जा रहा हूं, अगर ऑपोजिट डायरेक्शंस में करंट है, तो वो दोनों रिपेल करेंगे. इलेक्ट्रोस्टैट्स में ऑपोजिट चार्जेस अट्रैक्ट होते थे, यहां पे ऑपोजिट डायरेक्शंस में करंट अट्रैक्ट होगा. सो नाउ यू नो कि रिपेल होने वाला है, वो अट्रैक्ट नहीं होगा, क्योंकि करंट की बात कर रहे हैं. एंड दिस, as you can see in this figure, B is mu naught I 1.2 pi r. I did the same thing. What we also use is typically that since the wires are infinitely long, then वो current element को मैं हटाना चाहूँगा. I would want to remove that length element from my wire, because I really require the force per unit length, which is going to ease out my process, as then I'll simply multiply with the required length and get the force. So there's nothing much more to be said over here about this, apart from what you already know. So I know that force acting on 1 because of 2 is equal to the force acting because of 2 on 1, the magnitude part. Although the directions, if I am removing the magnitude, is going to be equal and opposite. So the direction part is going to be the opposite. And is it ringing some bells? Like आपको कुछ याद आ रहा है कि forces acting equal and opposite on different bodies? I've discussed this with you in one of my lectures of moving charges and magnetism, where I discussed about forces, as that was pretty much about forces. And forces, as Newton had told us, are always acting in pairs, and they are equal and opposite in direction and also on different bodies. न्यूटन का थर्ड लॉ यही था कि फोर्स एक बॉडी पे अगर मैं अप्लाई कर रहा हूं, देन वही फोर्स वो मेरे पे भी अप्लाई करेगा, इक्वल मैग्नीट्यूड में बट ऑपोजिट डायरेक्शन में. एंड इसका एप्लीकेशन एंड इसका रियल लाइफ एग्जाम्पल आप अभी इलेक्ट्रोस्टैट्स में और मैग्नेटिक फील्ड्स में देख रहे हैं. एंड I couldn't be more proud of this, because Sir Newton has told us the right thing yet once again. I never doubted him in the first place, but let's just take a moment of silence for Newton sir for giving us this. Alright, so I know that the forces are equal and opposite. Now what I also need to get done with is the force acting on any of the wires, doesn't really matter, they are the same, per unit length, which simply becomes mu naught I1 I2 upon 2 pi r. The distance between the wires is r. I1 and I2 are the currents which they are carrying. So the force acting per unit length because of the current carrying wires is going to be mu naught I1 I2 upon 2 pi r, which is pretty easy to understand, as they are going to be dependent on both the currents through both the wires and also dependent on the distance between the wires, as the force, the magnetic field, is dependent on the distance. And this is pretty explanatory self. And as you can see, आप लोग देख सकते हैं कि force acting per unit length is both I1 I2 और inversely depend करेगा उन दोनों के distance के बीच में. मेरा काम आसान इसलिए हो रहा है बिकॉज पर यूनिट लेंथ लेने से मैं इग्नोर कर रहा हूँ लेंथ वाला पार्ट इंटायरली, एंड मेरे को ये पता चल रहा है कि वो फोर्स अगर मैं एक लेंथ ले भी लूँगा तो उस पर कितना लग रहा होगा. सिंपल, रियली सिंपल. नाउ द मेन थिंग विच because of which I was discussing talk with you, as you have all guessed it, and as you can see that torque is a rotational force. वो उसको घुमाना चाहेगा एक current carrying loop को, and वो कैसे होगा is, as you can see over here, this is really interesting and a fun topic as well. And just be with me, be here. All those who are joining right now, just be along. We are going to do something really fun over here now, and this is so amazing because it involves torque, it involves electricity, it involves magnetic fields, so it is giving me everything I like together at once. क्या आपको कभी एक ऐसा पिज्जा खिलाया किसी ने जिसमें जो बर्गर जैसा दिखता है एंड उसके अंदर पास्ता भी है? दिस इज एग्जैक्टली व्हाट इट इज. ये मेरा ऐसा थाली है जिसमें मेरे को सब्जी, रोटी, दही, रायता एंड वॉट नॉट, मेरे को सब कुछ मिला, जो भी आपको अच्छा लगता है, वेज हो, नॉन वेज हो, वीगन हो, उसके हिसाब से वॉट एवर यू आर गेटिंग इज इट्स लाइक अ बुफे. आपको सब कुछ साथ में दे रहे हैं, एंड आई एम टोटली एंजॉयिंग दिस. मेरे को बहुत मजा आ रहा है. तो हो क्या रहा है, आई हैव दिस मैग्नेट ओवर हियर. So I have this magnet over here. North pole and the south poles are as follows. The monopoles don't exist, so this definitely has a south pole somewhere else. I can't see that, I don't know where it is, but maybe it's this one only. Maybe the magnet is connected from below. But anyways, we know that magnetic fields originate from the north pole and terminate on the south. We know that, right? We know it क्योंकि अर्थ का भी मैग्नेटिक फील्ड इज, we talk about Earth's magnetic field, but Earth का magnetic field is actually the geometrical north is actually the south pole of the Earth's actual magnetic field. That is why our compass points towards north, because यहाँ से fields जाके यहाँ जा रही है यहाँ से फील्ड जाके यहाँ जा रही है, terminating on the south. And my compass, which is also a magnetic iron piece, is going to point towards the south because the north is going to point towards the south, and it is going to tell me where the actual north is. So that is a separate chapter altogether, वो हम करेंगे बाद में. But अभी यहाँ पे what I have now is I have a current carrying loop, as this whole topic today is all about. A current carrying loop में a current I is flowing in. So if I'm looking from the top, the current is flowing in the clockwise direction like this. तो एक loop में एक current flow हो रहा है in a clockwise direction. And what is going to happen is that since the current carrying wires, it is comprised of 4 current carrying elements, or the current carrying conductors, and current carrying conductors are going to experience a force because of the magnetic field. We know that this force is going to be equal to I times L cross B. Since the force is going to be experienced by these wires, which we should calculate right now. Like, if you are not able to wait, so am I can't wait. Let's just find out. So north to south ki taraf, there's going to be a magnetic field. As you can see, the magnetic field is in this direction. Magnetic field throughout that loop is going to be in this direction. It's going to be the same for all of these separate wires as well. And the magnetic field is going to be in the plus I direction. So the B is equal to some K times I cap. Now the current through my first conductor, let's just say this is my wire 1, my wire 2, my wire 3, and my wire 4. So current is going to flow through my wire 1, and that is going to be in, so it's going straight. So let's just say that it is in the Z direction. So we are considering, so over here they are saying that this is Y. So it doesn't really matter, okay? We only need to find the direction of the force. So अगर current I straight जा रहा है उस conductor में, then I also know that there's going to be a force getting given by this formula of Lorentz, which is I into L cross B. So L is in the direction of my current carrying wire. अगर L सीधा है and B is towards the right, then I'm gonna keep my hand towards my L, curl it towards B, and the force given on that wire is being given by my thumb, which is right below, and वो नीचे की तरफ जा रहा है towards the center of the earth. Similarly, let's go on to the second wire. Second wire में the magnetic field is in this direction. The length vector is again in the same direction, and we know कि अगर एक charge की same direction में velocity के उस पे magnetic field भी लग रहा है. Similarly, if a current carrying element is being acted upon a magnetic field in the same direction of its length, no force is going to be experienced by it, as it's parallel to the B vector. So L is parallel to B vector, so L cross B is L into B into sine of 0, which is 0, as sine of 0 is 0. So the wire is not going to experience any force at all. Similarly, the fourth wire is not going to experience any force at all, as over here the L vector is anti-parallel to my B vector. And hence, I know that L and B are not going to produce any force because of the direction. Simply put, वो same direction में current जा रहा है तो या opposite direction में जा रहा है with the magnetic field, तो कोई force experience हो ही नहीं सकता. And since कोई force experience नहीं हो रहा, then I know कि 2 and 4 में no forces are there. So 2 and 4 experience no force. So 1 में I found out that the force is downwards. I'll just change the colors for the force really quickly. All right. The force is acting downwards. And similarly, for the fourth wire, the fourth part of this conductor, agar I is going towards me, it's coming towards me, the magnetic field is going to the right. I'll keep my hand towards L, curl it towards B, which is on the right. The force is going to be upwards. The force is going to come upward. It's going to go straight up. And perfect. This looks so beautiful, as now I have my entire setup in front of me. Looks a little dirty right now, but just a second, then I'll clean it up a little for you. Anything for you, anything for the love of physics, anything for making my life easier, and yeah, you know it all. All right, just getting rid of everything which is not part of this chapter. Alrighty. The force acting on the second element, or the third element, and the first element are equal and opposite in directions, as we just saw in the previous case. This is pretty trivial because I know that the current carrying elements are going to experience a force because they are kept in a magnetic field. जागृति, हेलो सर, गुड इवनिंग सर, आप बहुत अच्छा पढ़ाते हैं, मैंने आपके रिकॉर्डेड सेक्शन देखे हैं. थैंक यू जागृति, आई फील रियली empowered by hearing these comments. Prakash Kumar, good evening to you as well. Just stick along, we are finishing this section of this chapter, and soon, like in the next class, we are going to get done with this chapter as well. And उसके बाद I'm going to just do one consolidation session जिसमें we are going to discuss some leftover topics, and then we are done. उसके बाद the next chapter I'm going to do is the electromagnetic induction, which is again brilliant chapter, one of my favorites. And soon we are going to get done with the term 1, and मैं एक और session भी आपको start करने वाला हूँ आप लोगों के लिए. I'll keep that as a surprise for now, but let's move on. So 2 and 4 experience no force. 2 is this one, 4 is this one, as the force is not going to act on these, as the magnetic field is in the same direction as the length vector of these wires. And what is going to happen now is that only 1 and 3rd, the 1 and the 3rd wires are going to experience force which are opposite in directions. The net force acting on. So let's just look at the free body diagram of this current carrying coil. It experiencing a force F upwards, the same force F is downwards. The net force acting is going to be 0. So the wire is going to stay there right at the place where I'm keeping it. Even if I'm keeping it with a support, it's not going to move from that position, as you all know that if the net force acting on a body is 0, then it is going to stay at the same state of motion or rest, which is told by Newton's laws of motion. And similarly, Newton didn't speak much about the rotational laws of motion, but we also know that if there's a force acting about an axis from a distance r from it, then it is definitely going to produce a torque about that axis. This is the same example which I gave to you in the beginning of my class, as what when you push a door through a doorknob, it is going to open up, right? अगर आप दरवाजे को यहाँ से खोलेंगे तो वो दरवाजा तो खुलेगा ही. यहाँ पे बस मैं फोर्स ऊपर लगा रहा हूँ तो वो एक्सिस के अबाउट तो घूमेगा ही. ये करंट कैरिंग वायर को, इस करंट कैरिंग लूप को इमेजिन इट एज अ डोर विद द एक्सिस थ्रू द मिडल. आपने ऐसा दरवाजा शायद ना देखा हो. मेरे पुराने घर में, एंड लाइक द सेम हाउस वेयर आई एम इन राइट नाउ, उसमें एक दरवाजा था जो बीच से भी खुलता था, एंड वी हैड टू गेट रिड ऑफ इट बिकॉज वो बहुत पुराना हो गया था, लाइक ओल्ड टेक्नोलॉजी, नो वन यूजेस दैट. बट दिस रिमाइंड्स मी ऑफ दैट कि वी आर पुशिंग द डोर एंड उसका एक्सिस बीच में है उसके, सो द डोर इज गोइंग टू मूव लाइक दिस. समझ रहे हो आप? लाइक बीच से वो हिलेगा एंड it's going to rotate about that axis which is going through the center of the door. So that is the amazing part, that यहाँ पे net force is 0, but net torque is not zero at all. In fact, it is pretty much there. It is a big enough thing, and that is going to make, so as you can see, there's an omega over here, so that omega is going to be generated because the net torque is going to generate some net alpha. Net angular acceleration is going to generate some net angular velocity, and net angular velocity is going to generate some net displacement theta, like the rotational angle, which means that the object is rotating. And I gave you a brief in the beginning of the class just to repeat myself over here once again, because I love to repeat myself when it comes to physics, not otherwise, but only in physics. So net torque is not zero, but net torque is not zero, but the net force is definitely zero. And net torque is now what we need to find out. So torque, as I already told you, is R cross F, where R is nothing but the moment arm or the distance of the current carrying wire from the axis. प्रकाश कुमार कह रहे हैं जीरो, हाँ नेट फोर्स जीरो है, परफेक्ट. जागृति कह रही है सर हिंदी में ज़्यादा अच्छे से समझ आता है. देखो जागृति और प्रकाश, मैं हिंदी इंग्लिश आई डोंट केयर अबाउट द लैंग्वेज, आई एम गोना स्पीक इन फिजिक्स. मैं इस तरीके से बात करने वाला हूँ कि आपको जो भी मैं बोल रहा हूँ समझ आ जाएगा, बिकॉज ऑल आई एम सेइंग इज इन फिजिक्स. अगर आपको लैंग्वेज की प्रॉब्लम आ रही है देन आई मेक श्योर कि मैं अगर कुछ कॉम्प्लिकेटेड बोल रहा हूँ इंग्लिश में देन आई विल से द सेम थिंग इन हिंदी एज वेल. तो नथिंग टू वरी अबाउट, जस्ट टेक अलोंग. फिजिक्स समझना इंपॉर्टेंट है, लैंग्वेज समझने के लिए तो हिंदी इंग्लिश की क्लासेस लगा लो, लाइक दिस इज नॉट फॉर दैट. एंड मूविंग ऑन, आगे बढ़ते हैं. टॉर्क इज आर क्रॉस एफ, वेयर आर इज द मोमेंट आर्म. मोमेंट आर्म मतलब दिस परपेंडिकुलर डिस्टेंस फ्रॉम माई वायर फ्रॉम द एक्सिस. आर क्रॉस एफ इज simply just rf into sine theta, where r sine theta clubbed together is going to give me the perpendicular distance from my wire. Agar r is the distance from the wire, then r sine theta is going to give me the perpendicular distance, and cross product is hence so useful because we are using only the perpendicular part component of one vector multiplied with the other vector. Ye the essence and the values of vectors q इतनी अमेजिंग चीज़ है. लाइक क्यू वो हमेशा मेरे को अमेज करने से कभी भी दे नेवर सीज टू अमेज मी, बिकॉज दे वर डिजाइन्ड इन अ वे दैट वी कैन मेक गुड यूज ऑफ देम इन फिजिक्स. एंड आई हैव डिस्कस्ड अबाउट द एसेंस ऑफ वेक्टर्स इन माई इंट्रोडक्टरी लेक्चर. यू कैन चेक दैट आउट. बट फॉर नाउ लेट्स जस्ट फाइंड आउट के इफ दिस डिस्टेंस इज r, so what is the torque acting because of this force F? I know that this r vector, this r value is y by 2, as the total distance is y, so I know okay uska half is y by 2, so y by 2 times F is the torque acting on the element 3. Similarly, the torque acting on element 1 is again y by 2 into F. The key thing over here is to note down the direction, and the direction of a vector, the cross product, is given by the right hand thumb rule. So agar F is acting upwards, I is coming thiswards, the r vector is going outwards, so the r cross F is going to give me a direction like this. The key thing, the important thing to note over here is Jagriti and Prakash, ये key thing, important thing note करो के जो डायरेक्शन टॉर्क की होती है वही डायरेक्शन एंगुलर वेलोसिटी, एंगुलर एक्सेलरेशन एंड इवन एंगुलर डिस्प्लेसमेंट की भी होती है. तो इफ आई एम सेइंग दैट द ऑब्जेक्ट इज रोटेटिंग लाइक दिस, अगर ये पूरा सेटअप ऐसे रोटेट कर रहा है तो मैं बस अपनी उंगलियों को इस डायरेक्शन में कर्ल करूंगा एंड मेरा थंब इज गोइंग टू गिव मी द डायरेक्शन इन विच माई टॉर्क, माई ओमेगा, माई अल्फा, माई थीटा एंड ऑल दीज सर्कुलर कॉन्सेप्ट्स are having the direction in. तो ये बाहर की तरफ आ रहा है, मेरी तरफ आ रहा है, and I can say that अगर ये z direction है then the torque, omega, alpha, so on are all in the plus k cap direction. इस केस में force is upwards, r is this direction, so r cross f comes outwards. But for the first element, so this I can say that it is in k cap, but for the first element the force is downwards. Force यहाँ नीचे है. एक minute, I'll just make things beautiful for you because you are also beautiful, so why not. So force is acting downwards, my r vector is leftwards. R is nothing but the position vector of the lever arm axis से towards my wire. Remember this, position vector is defined from an origin or from an axis and it goes towards the wire. Once again, watch my previous lessons to get to know about position vectors. I believe my first lecture, which was Welcome to Easy World Physics, is where I discussed about everything, which could be a little confusing for you, but now it's not. So again, force is downwards, r is in this direction. Keep my hand in the direction of r, curl it towards f. I again find that the torque is coming towards me. So ये दोनों torques are acting in the same direction and they are going to give me the same torque in the same direction. So इन दोनों का torque is going to add up together. They are helping each other out. अगर इसकी वजह से ऐसे घूम रहा है, वह नीचे वाले फोर्स की वजह से भी ऐसे ही घूम रहा है. So the omega or the acceleration because of both these forces is going to be in the same circular direction, which is like this. And उसकी direction is actually k cap because circle की vector direction is given by the right hand thumb rule. मेरा thumb is going to give me the direction. Clear? Easy था. K cap. दोनों k cap में है तो y by 2 into f plus y by 2 into f. So my net force is going to be y times f in the k cap. Sorry, my net torque as given in the vector form is y into f cap. I hope you all are well versed with what torque is and how to apply torque. And just have some water now because staying hydrated is really essential. And I'm not saying this because I don't get enough water, but in general you should drink at least 2-3 liters because it's good for you. Although definitely Africa mein there's much more requirement of water and I wouldn't want to drink a lot so that वहाँ पे कम हो जाए. But I don't think that's going to be the case. तो आगे बढ़ते हैं. अब oopsies, 1 second. All right. Just a second. All right. तो ये था what is the torque being calculated on this wire. Now we also know that the force, as we all just did, is actually just going to be the current I times L times B, isn't it? B I know, I know, L I know. L is the direction, L is the length vector which is in the forward direction of the current. B is in the direction of the magnets and force is calculated by ILB, where IL cross B is just essentially giving me the direction. So I found out that force की directions are upwards and downwards. Because of this, I know that Y into F, so Y into F is ILB and यहाँ पे L and Y को मैं क्लब कर सकता हूँ. अगर Y is this distance, L is this distance, so this is essentially forming a rectangle with the dimensions L and B, right? L and Y, तो L and Y की dimensions वाला एक rectangle मिल गया, उनको मैं multiply कर रहा हूँ तो वो area देगा उसका, because that's what area is. It's the length into the breadth. And whichever the length and breadth may be, but I now know that this is going to give me the I times area times B, where A is nothing but the area of my loop. तो मज़ा ही नहीं आ गया क्या? मेरे को तो बहुत ज़्यादा है. आई एम फाइंडिंग दिस रियली रियली फन बिकॉज सब कुछ, एवरीथिंग इज अलाइनिंग इन टू प्लेस, everything is just falling into place, and I know what is what is happening actually when I'm passing current through a current carrying loop which is in a magnetic field. So these figures might give you a better idea of what we are dealing with right now. What it is showing is essentially के so यहाँ पे भी एक magnetic है north pole, यहाँ पे एक magnet है south pole का, and I know कि magnetic field is going from north to the south, and also since magnet field is going from north to the south, the force acting on this current carrying element, इस case में the direction is opposite, so the force acting over here is going to be upwards while the force acting on this is downwards. And if it's acting like this, then the wire is going to rotate again, and the angle which my forces, which are always downwards or upwards, is making with my magnetic field is given by theta. I can also say that this area vector ka direction is perpendicular to my plane's direction, and the angle made by my b vector and my a vector is theta. So a vector and b vector are at an angle theta. Now you might ask me that what is the way to find out the direction of the area vector? It's simply given by the right hand thumb rule. Wherever you are confused, just apply the right hand thumb rule, because that is the key rule and that is what we are going to use all the time for finding any directions whatsoever. Agar curl kar rahe ho, then the thumb is going to give you a direction. Agar thumb use kar rahe ho, then the curling of the fingers is going to give you the direction. And hence, I know okay, if the wire is going, the current is going in this direction, so I'm going to curl my fingers towards this direction, and the area vector is going to given to me by the thumb's direction, which is downwards. So as you can see that this is the direction of the area vector, and similarly I find the direction of the magnetic field, and the forces are like this, so the torque is going to be like this, and this is how this figure is looking like. Now a simple problem time which I'll pass on to you as a homework. And what I'm having now is that I'll just give you a coil. Okay, so now we are studying about the coil. Let's just say that it is having n turns. So instead of one turn, I'm giving you n turns, which is maybe gonna take you n chances to get to the right answer, but not really. It's gonna take you only one. So n turns ka coil. I also have magnetic field B. Let's just say the current it is carrying is I, and also the so what I need to find out now is that what is the angular speed omega. This is a problem right from your NCERT textbooks. And what is the angular speed omega when coil rotates 90 degrees? So I'm giving you all the required information. Ke n turns is coil ke, B is the magnetic field passing through the coil, I is the current flowing inside it. What is the omega when the coil rotates 90 degrees? And I also am going to provide to you the moment of inertia I. So these are two separate things. This is the current And let's just say that this is the I dash, or the moment of inertia. So moment of inertia is coming into play because I need to find out the omega, right? अब यहाँ पे एक और एग्जांपल है. I'm going to explain to you why we were talking at all about the stable and the unstable equilibriums. You forgot about that, right? I did not. I know, okay, this had some implications, and the reason why we are doing the stable and the unstable equilibrium was because in this case, just look at the coil. This is kept in a different direction this time. So the omega and the torque is going to be like this over here, because my L is not in the plane of the magnetic field, but it is in the other plane, and it's actually in the Y, it's in the Z plane. So my force acting will be in the different direction than the previous example, but the concept doesn't change at all. The concept is going to be still the same. The only thing that is different is the rotation ka direction, which is also going to be about the axis, as it's all self implied. And what is the key thing which we need to do, which we really need to learn about in this current carrying coil, is the stable and the unstable equilibrium. So what happens is that it can be explained by any example. So I'm just going to stick to this one. So just hang out with me for this once. We are going to be done with the lesson in no time now. I know that the force acting on this wire and on this wire is going to give it a rotation like this. But I also know that as the coil keeps on rotating, so if I'm keeping my coil right over here, then the torque is going to act in these two directions. But as my coil starts rotating, there's going to be some difference of the torque that is acting on the current carrying loop. The reason being, there's a change in the angle theta, and the angle theta, if it's changing, then the distance. So if this angle is now theta, this distance is not going to be y by 2, but so y by 2 was the distance when my theta was 0, or the initial configuration. But now, since it has rotated by an angle theta, the distance y by 2 changes into something else, which you can find out by trigonometry. As we all know that this length is y by 2, which is the length of the half of my coil. The distance from the axis to the wire is y by 2. It is fixed. This angle is theta, so this angle is also theta. And I know that sine of theta is going to be is opposite upon hypotenuse. So opposite side is this side. Which is my required side, right? This is my R vector, which is because of which the torque is acting on that circular framework. So sine theta is going to be the opposite R vector, which I need to find out, upon the hypotenuse, which is y by 2. So sine theta is R upon y by 2, and R vector is simply y by 2 into sine theta. And now I know that the torque is going to be, instead of IAB, this Y wala section is going to actually get changed by a factor of y sine theta, where theta is the angle between the area vector given by my right hand thumb rule and the magnetic field. And the angle between the magnetic field and the area vector is going to keep on increasing as my coil is going to keep on rotating. So now the angle is, so since my area vector is going to be in the direction of the loop, the area vector is in this direction, the magnetic field is in this direction. Now, since my area vector is going to rotate, the angle which is going to be made with the normal is going to change, right? The angle is going to keep on changing, keep on increasing till it becomes 90. At this point, sine of 90 is 0. So the torque acting on this current carrying loop is also 0. And now it's again going to change, again going to change, again going to increase. And once the angle becomes 180, the torque is going to act in the opposite direction, because sine of 180 is minus 1, but also I know that the wires have now interchanged. The wire which was carrying current in the inverse direction is now going to carry current, well, yet again in the inverse direction only, but it's going to act in the torque acting on it is going to be in the opposite direction, which is the key part, which is the fun thing over here. As since I know that the area vector is going to make an angle theta with my magnetic field, the angle is going to keep on changing, and if that angle theta is increasing, then I'm going to say that at the 90th, if the angle becomes 90, the torque is 0, and if the angle becomes 270, the torque is 0, because by trigonometry, and because you all also know that if it's going to be in the plane. So let's look at this. If my current carrying loop is making an angle of, well, 90 now from the perpendicular, the forces acting on the wires are going to be passing right through my axis. And what happens when the forces are passing right through my axis? If I'm taking this, for example, if I have this phone, if I start pulling it from both these directions, it is not going to rotate, right? Although if I push it from here and pull it from here, it is going to rotate. Although now I'm going to push it from here and pull it from here, it is going to stop rotating. Just look at it once again. Easy visualization, but really fun. If I have this phone, if I'm pushing it from below, and if I'm pulling it from here, so from here I'm pulling, from here I'm pushing, then it's going to rotate. But from now onwards, after the angle becomes 90, I'm going to push it from here. The force is going to act in the same direction, as nothing is changing. I is the same direction, B is in the same direction, L cross B is also going to be in the same direction. So if I'm going to push it from upwards, pull it from below, it is not going to move at all. It is going to stay here. But since this is having some angular velocity beforehand, it is going to overshoot from here, and then after that I'm going to apply the force in this direction. The force is going to be in the same direction. Key thing to note is that the force is always going to be in the same direction on that specific wire which I'm choosing, and if I'm applying force in this direction, then it is going to come back again. So you can see what is happening with this current carrying coil. Can you observe what is this? What kind of motion is this? This is a simple oscillatory motion, which we discovered, which we relearned in the beginning of the class for a particular reason, which was this, which is why we are doing this. The most amazing part over here is that my force acting on my wires is going to rotate it like this in an oscillatory kind of a motion. What this median position where theta is 90 with the perpendicular, with the axis, is known as a stable equilibrium, as the torque about it is going to take it back to the initial configuration. But if I rotate it furthermore to 270 degrees, then the torque acting is going to, this force is going to be pulling, this force is going to be acting downwards, this force is going to be acting upward, and the force direction is not changing. तो अगर force की direction नहीं change हो रहा है तो ये pull करेगा, push करेगा, and it is going to come back up. तो ये एक unstable equilibrium हो गया. Are you able to feel it? इसकी feeling आ रही है? Force की direction is going to be in the same direction all the time. Mark my words, force is going to be always in the same direction, because उस wire में current is going in the same direction, the magnetic field is in the same direction, तो force is also going to be in the same direction. तो एक wire पे ऊपर, एक wire पे नीचे. अगर वो wire ऊपर आ गई, if that wire is now directly above it, तो मैं इस फोन को यहाँ से खींच रहा हूँ, यहाँ से नीचे से पुल कर रहा हूँ, तो अगर मैं इसको थोड़ा सा टिल्ट करूंगा तो it's going to be a simple oscillatory motion, and the phone is not going to move about this stable equilibrium. It is going to tend to stay right where it is, which is near the axis. And if by momentum the phone rotates even more, यहाँ पे this force is acting upwards, so ये force ऊपर है, ये force नीचे है, तो ये अभी भी उसको उसी डायरेक्शन में लेके आना चाहता है. But if it rotates even more, तो यहाँ पे भी the net torque acting on this phone is zero, as this force is acting downwards, this force is acting upwards, but they are both crossing my axis, so my phone is not going to rotate at all. My phone is going to stay there, but ये फोर्स दबाएगी इसको, ये फोर्स ऊपर करेगी, तो ये एक अनस्टेबल इक्विलिब्रियम है. अगर मैं थोड़ा सा भी फोन साइड में करूंगा तो यू सी, थोड़ा सा भी साइड पे, अगर इस साइड भी करूं, दिस इज going to make it rotate in an instant like this. This is what an unstable equilibrium is. Unstable equilibrium की feel अब आ रही होगी, just like this ball lying on the top of the cell. Stable equilibrium की feel भी आ गई because the ball lying on the bottom of the cell, and neutral पे तो वो आया ही नहीं कभी. And since if you are just joining with me right now, just go through my lesson where I was explaining to you कि कैसे torque से this tumbler is going to topple about, and the same scenario is with my current carrying loop as well. तो यहाँ पे we discussed about the angle theta, which is the area vector's angle, and we are also going to discuss this homework problem with you, in which I'm giving you all the required terms for which you need to find out the omega when the coil rotates 90 degrees. And the theta के बारे में we are going to discuss more, because it is an entirely different concept, the magnetic moment, which is going to be my next lecture. But till then, you are all having enough to absorb in, just let it all sink in, and come on Unacademy Plus, because here you're going to get regular doubt clearing sessions from top educators on one platform, from the comfort of your house, with a mentorship, guidance, practice tests, PDF formats, live test series, and you'll also be kept in a batch. You are also going to become a part of a batch. Like if you're not going to school right now, you'll be a part of that school. And the prices are as follows: for 2 months or for 2 years, you are going to get 1,042 only, and 10% off milega if you use my coupon code SIDS10. For 1 year, it's 1,250. And अगर आप चाहते हैं कि I communicate directly with your parents one-to-one, and not with your parents, I don't want to do that much because I know you're going to do great, but also with you. If you want me to be your personal mentor and be with you in the entire time and just help you sail through your journey of this 11th, 12th grades, and which is going to be so great. Not kidding you, but then you need to take the Unacademy Iconic. The prices are going to be 2,000 and 2,333 a month, which is not much considering what you're getting. The features are phenomenal. They are not like something which you get for like really less prices, but here they are. Believe it or not, this is how the platform looks like. You are going to get the questions in the question tabs, live polls, poll leaderboard. So it's a gamified experience for learning, which is the future of learning and the future of technology. Why not go for it? You can join the test by using these steps, and again the steps are as follows. The special class timetable I'm going to share with you later on, but the upcoming batches for CBSE 12th and CBSE class 11th are also as follows. And the Shera Dhamaka offer, the Shera is in the air, and we are all excited. It's valid till 18th October, which is the best thing because it's valid till even after the Shera, and you can Like, who doesn't want an extra 4, 6, and 8 months of free education? No one. I'll not kid you. No one. No one would not want that. And you'll definitely go. You should definitely go for it. Go for it. So, as you can see, these are the respective months for which you'll get these respective offers. And with that, thank you. Namaste. A very happy Dussehra to all of you, and use my coupon code SIDS10 once again to get a 10% discount on the already discounted amounts. As you all know, you know the drill. Like, share, subscribe, press the bell icon. Just get notified with whatever Unacademy Scholars is getting at your doorstep. And you all know, with scholars, with me, with you, with the entire universe, the power is going to get together, and the conspiracy says that we are all going to crack it. So let's do it. Now let's get out of here. Have fun. Tomorrow is the Dussehra, but keep me posted on what you're thinking. I'll keep you posted, and we are gonna get done with this physics thing in no time. We are gonna have fun. See ya later. Bye bye.